Alright, now question 3 asks us to state an insertion criteria that will allow the binary search tree to remain balanced.
So you need to put another.
So the question is, if we had the ability to reorganize our values and then insert these values in an order of our choosing, how could you insert the values so that the tree remains balanced?
I put something else back where I should put into from.
But I'm not really asking for the technique, I'm just asking for the criteria. Basically, since we don't have a lot of time, I'll just tell you. If you're inserting such that the next value to be inserted is the median of the remaining values, median meaning the middle value, then the tree will be guaranteed to be balanced. So for each value, then that condition must hold true. Now, suppose we want to make sure a binary search tree behaves badly. What do we need to do with the data to make sure that it's totally unbalanced?
Just find the highest number.
We sort it. If the data is inserted in sorted order, then the binary search tree will be completely unbalanced. Alright, now before we move on, especially since some of you are doing work on the project now, there's a concept that I think I need you guys to absorb, and basically that's how you'd write the scheme code to build a certain tree. So let's say we're going to implement our tree as a set of nodes, and each node is based on a list. So we can say we have a scheme function, make bin tree, and we'll pass some arguments for root left and right. And these are values that are supposed to be inserted as root left and right. And then you can actually insert what you want there, what these values into a list. The list with root as the first item in the list, left as the second, and right as the third. Of course, since it is your function, it will be totally up to you to change over those functions. You'd have seen code like that in the project you're working on. Now, let's say I had something to describe the empty tree as an empty list. Now, suppose I wanted to create a tree with these values. How would I do it? What scheme code would I write to create a tree that would have a node with 4 at the root, followed by a node with 6 on the right subtree?
So this root, and then in a separate line you're gonna have this left. Is that left, right?
Well, first I define this node for the empty tree, for the root, and it would have 4 as the root, the empty tree as the left subtree, and another binary tree as the right subtree. Now this binary tree would have 6 as the root, the empty tree as the left, and the empty tree as the right.
Okay, it continues like that. It continues like that.
Well, in this case, we need only 2 nodes. So if I am actually creating that structure, I would go let's call it T as make bin tree my root should have value 4. My left subtree would be the empty tree. And my right subtree would be another node, so I'm going to call make bin tree for that. Or rather, alright, not just another node. Remember, a tree is a root with a left subtree and a right subtree. Also remember that. So this right subtree needs to be defined as make bin tree and at the root of that right subtree we have the value 6. The left subtree would be the empty tree. And the right subtree would be the empty tree. Who's with us? Is
no, nobody's not there.
Nobody's not there.
Nobody didn't answer. So you have bin tree 4. Make binary tree 4. The empty tree. So we didn't tell the because 6 is going to be another root. That's why we have it there. Is that it?
Right. Always remember the formal definition of a tree. When you think of a tree, what you're really thinking of is a root and a tree over to the left and a tree over to the right. It's just a tree over to the left will stand with a root there. Alright, so
you have left and right, but we haven't used them over there any at all.
Why do you think you haven't used it?
I mean,
what do you mean when you say haven't used it?
You have left.
What do you mean the variables left and right?
Yes, we're not using them any at all.
We have passed the arguments to the function. So if we had needed to do a traversal, maybe to find something in the tree, then maybe we could have used left and right. But right now, we're just creating the tree, so we're just calling make bin tree with the arguments to put values in place.
So you get my practical. Okay,
Alright, so as you may have seen before, we have several different tree rules. The binary search tree is just one of them. Now, the generic binary tree is just simply a root, because it's just a root and a left subtree and a right subtree. When we say we're making a binary search tree, we have started with a binary tree and we put rules on it. Right? Now, there's another binary tree that you guys will meet, or you have met, and that's a binary heap. Now, the heap is a binary tree with a partial ordered property that is what you call left complete. So the partial ordered property means that once you insert a value in the tree, you're going to make sure that the smaller values are always above. And to make it left complete in each level, once you're filling the values are inserted in left to right order. We're going to insert these values into a heap. So we'll insert to heap. And the minimizing binary heap means that the smaller values are on top. You could also have a maximizing binary heap which puts the larger values on top. But in this course, we're using minimizing binary heaps. So we're going to start by inserting 5. And for these, I'm going to insist that we do each one step at a time and write out the whole thing. So we're going to insert 5. Of course, we end up with one node with 5. We're then going to insert 2. So we start the insertion procedure by tagging on the new value to the position that it goes in first and then fixing if necessary. So the partial order property is violated here, so then we need to swap. Which gives us 2. Then we're going to insert 30. 2, then 5, then 30. Are we done at that level? Mm-hmm. Then we're going to insert 20. Then 2, then 5, then 30. Next position is next level. 20. Then we're going to insert 15. So start with our 2, 5. Then we're going to insert 1. And the 1 goes here, right? So are we done?
Yeah.
We're done.
Say the foolishness.
No, I didn't. I started doing something, but
Where's
maybe I'm not finished.
So where's the 20 over
Stop.
there?
What? Where's the 20 over here?
The 20 is on the left hand side instead of the right.
Okay, slow down. Let's go back to right here. Remember that we have several different rules that we're working with for the different data structures, right? Now, remember the binary search tree. We've done the binary search tree. We're not doing the binary search tree. No, we're doing the binary heap. So, when we had, I'm sure you agree with this insert, right? You agree with this step after inserting the 20? And the 20 has not moved, so I'm not sure why you asked me why the 20 was there.
I'm thinking back to binary search.
Okay, so you're confused. But you agree with where the 20 is now. So okay, so we inserted the 15. Do we agree? That that's where the 15 will go? We inserted the 1. Do we agree that that's where we put the 1 first? At first?
Yeah.
At first, that's the next insertion position, so we'll put it there.
Right.
But is there something else we need to do?
Move up to the top.
We need to compare the value of the parent and swap if necessary. So we're going to do a swap. Which will give us 2,
5, 1.
The space here is not enough, so and it's the second to last step, so I can come over here. 2, 5,
31 and 13, goes above 30. Because he's swapping them.
No, I didn't want to understand up on this.
Well, I think we're supposed to try to keep the tree balance.
Right.
I heard that answer, I'm not sure I agree with it. The question was why
is the 1 on that side instead of not where the 15 is?
Because in a heap we know exactly where we're going to insert. We fill the row completely.
So
it says what's that?
So we get it balanced.
Exactly.
And that's what
So
you
that's
said.
what I said, sir. You see, did I agree?
No, but okay, fine.
No, I was looking
But
for something else from her because of the external notes that you always. It's an imaginary. I know it's supposed to be there, but we have not drawn it.
Okay, cool.
Right.
Okay, so once the next insertion position, we fill all the rows from left to right. So that's the next insertion position. Well, as an end result of you inserting like that is it's balanced, yes. Now, you then need to fix to make sure that you meet the partial ordering property. So you do that swap there, come here, and then you check the parent to see if we need to swap again. Do we?
Yeah.
Because the parent is larger, the parent needs to be smaller if we're going to be happy. So we're going to swap here again. So we end up with 1,
5, 2, 15, 2, 30.
And that's our heap. Now, a couple of things that we can take away from this. If we have n items, we know that the height is log to the base 2 of n, right? Because the tree will remain balanced. So, how many steps do we have to go through to, how many swaps would we have to do to fix the heap?
3.
In this case, we'll do up to 2 swaps, but generally, if we have n items, let's say the height of the tree is h. In the worst case, how many swaps would we have to do? H swaps. And because the tree is balanced, h is log to the base. So we're guaranteed a performance of the heap of log to the base 2 of n. Once we look at all the operations that need to happen for insertion and deletion.